Welcome back, and we're going to continue our look across period 3, but this time we're going to be looking at the chlorides, not the oxides. So let's get going. So when we look at the period 3 chlorides, we can look at them in the same way we did with the oxides, in that we can look at their physical states and the bonding that gives rise to that. So you need to be able to know what their physical states are under standard conditions, the electrical conductivity of these substances, and then look at some of the specific properties of known compounds. So if we look at our chlorides, we see that we have sodium chloride, magnesium chloride, aluminium chloride, silicon chloride, phosphorus chloride, sulfur chloride, and then chlorine. As we saw with the oxides, we tend to see ionic compounds forming in group 1 and 2. We get an ionic lattice structure, a layer lattice structure with aluminium chloride. We get covalent molecular, but not giant molecular, discrete molecular for silicon, in this case with chloride, in contrast to the silicon dioxide, which was a covalent molecular lattice. And then PCl5, covalent molecular, SCl2, covalent molecular, and of course Cl2 is a covalent molecular with weak dispersion forces only. As you can see here, our boiling point tends to decrease, or melting point and boiling point decreases as we move across the period, starting with 801 with the strongest lattice enthalpy with sodium chloride, moving to 714 with the magnesium chloride, and then we have sublimation with AlCl3, so we don't actually get to the liquid, it goes straight from the solid to the gas. Then we start to see our melting points drop significantly with -70 for silicon. Our phosphorus jumps back up to 179, very close to that of aluminium chloride, but then we see a rapid jump again down to -121 and -101. So these -1s are clearly going to be gases at room temperature. So we'll have solids for our ionic, sodium chloride, magnesium chloride, and aluminium chloride. Then when we start to get to our covalent compounds, we are seeing liquids and gases, with the exception being PCl5. So aluminium chloride is actually quite unique. It forms a layer lattice. Under standard pressure and temperature, standard pressure, it sublimes at 178. If you get it at very low pressures, though, you can cause it to melt. The structure changes once it's melted to have a covalent structure, which is quite unique and unusual, and it forms a dimer with two dative covalent bonds, as we've seen shown in this diagram here, where the covalent bond is actually being formed by the chlorine donating both electrons to the aluminium and forming this square dimer structure. It doesn't conduct electricity in a molten state, as it has covalent molecular bonding in this state, so that's an exception to make a note of. Silicon chloride, as we're shown here, has a tetrahedral shape. It therefore forms discrete covalent molecules with weak dispersion forces because it is non-polar. It's typically a liquid under standard conditions. Sulfur dichloride, again, is covalent molecular. It will have a bent geometry due to the lone pairs present on the central sulfur atom, bonding out to chlorines which have their standard octet, forming only one bond. This is a liquid under standard conditions because we will have dipole-dipole interactions, and overall the molecule will be polar, though you should check the electronegativity differences to confirm this. Phosphorus chlorides come in a number of different structures, including some of the new molecular geometries that we've found. PCl3 will have a trigonal pyramidal geometry, whereas where we see PCl5, we now have our trigonal bipyramidal. They're covalent molecular compounds, with phosphorus 3 chloride being the PCl3, being trigonal pyramidal, slightly polar, and will have dipole-dipole interactions, which leads it to being a liquid under standard conditions. Phosphorus 5 chloride is our trigonal bipyramidal. It is non-polar, has strong dispersion forces, Because it is large and the number of electrons and the number of chlorines in here, the dispersion forces are quite strong, and this will be a solid under standard conditions. Even though technically it has the weaker type of dispersion force, those dispersion forces will be stronger than the dipole-dipole exhibited by the weakly polar PCl3. So our period 3 chlorides, they are solids at room temperature up until our SiCl4, where we start to see liquids and gases form. The bonding is ionic for group 1 and 2 chlorides. After that, it is covalent for all others, remembering that aluminium chloride is ionic at the solid layer lattice. Once we melt it, however, the bonding becomes covalent in the formation of the dimers. Structures are giant ionic structures for group 1 and 2, and molecular compounds for group 13 through to 17. Only the ionic compounds will conduct, and this is only when they are molten. The electrical conductivity is pretty much non-existent or poor for the others because they are uncharged neutral compounds. As with our oxides, these have acid and base characters. NaCl, the Na plus and Cl minus, neither have a very strong acid or base character, so this is a neutral salt. Magnesium chloride is a slightly acidic salt, but only slightly. Whereas our Al2Cl6, SiCl4, and phosphorus chlorides, as well as chlorine, are all acidic chlorides. So when we look at the reaction of ionic chlorides with water, of course, we know that NaCl will dissociate, forming aqueous ions, of which are soluble, forming the hydrated ions in solution. Same with magnesium chloride. These are both soluble chlorides. Magnesium chloride is a small molecule with a greater charge, however, so it is able to have a dative bond between the magnesium 2+ and water molecules. We'll learn about these a little bit more later on when we look at our HL acids and bases, but essentially this is giving it Lewis base and Lewis acid characteristics. So it will act as a Lewis acid, forming a hydrated magnesium complex and 2Cl-. When we look at aluminium chloride with water, the aluminium chloride will react with water to form aluminium hydroxide and HCl. So we actually get hydroxides and HCl forming. When we react with a large excess of water, the ACl3 dissolves and acts as a Lewis acid. And a Lewis acid essentially accepts a lone pair from the electrons in the water, forming our aluminium complex that we saw before, which is a complexed ion, which we'll again learn about a little bit later on. The hydrated ion can then go on to act as a Bronsted-Lowry acid and donate a proton, resulting in the acidic solution. So it's a three-stage process. The aluminium chloride reacts with water to form aluminium hydroxide and 3HCl, which would be neutral. The aluminium chloride can react with an excess of water, forming the aluminium water complex, and then that complex can react with excess water, where the water will act as a base, and we will form an equivalent of H3O+. So when we talk about the formation of a Bronsted-Lowry acid, we are forming something that is able to be able to donate a proton. The initial step is AlCl3 acting as a Lewis acid, i.e. a metal ion that gets a dative bond. It accepts a electron pair. When the complex is formed, the hydrated aluminium ion that we see with the 6 water molecules around it, one of those water molecules is able to donate a H+, leaving the complex, the hydrated complex, having donated a proton. So this means that it will have more H3O+ in solution, so it is acted as a Bronsted-Lowry acid in this case. When we look at covalent chlorides with water, okay, so this be SiCl4, PCl3, PCl5, or Cl2, All of these will react with water to form their corresponding acids. SiCl4 will actually form 4 equivalents of HCl, and then silicon dioxide solid will precipitate out. Whereas PCl3 will form HCl plus H3PO3. PCl5 will form 5 lots of hydrochloric acid and H3PO4. And then chlorine will form hypochlorous acid. You should make a note of each of these reactions in your notes. So in summary, sodium chloride dissolves readily. We know that. It's a highly soluble salt. The polar water molecules are able to stabilize the positive charge and the negative charge as they form the solvation spheres. Magnesium chloride and aluminium trichloride will form acidic solutions due to their small, highly charged cations, drawing water molecules to form complex ions. These complex ions are then able to give up a hydrogen to other water molecules that are surrounding the complex, making them acidic. ACl3 will also form HCl when it reacts with water. And then our molecular chlorides all react rapidly and quite violently with water to form hydrochloric acid in exothermic reactions. And that's it. That is the trends and the equations that we need to know. There is quite a few. Make sure you have them in your notes for the period 3 trends for HL. And I'll see you in class.